Welcome to the deep dive. Today, we're plunging into, well, one of the universe's most fascinating and, frankly, weirdest subjects, black holes.
Absolutely. They capture the imagination like few other things in cosmology.
And I think when most people imagine a black hole, they probably picture, some kind of cosmic vacuum cleaner just hoovering up everything nearby. Is that right?
That's the classic image, definitely. But it's a really big oversimplification. Actually, it's mostly wrong.
Oh, how so?
Well, the surprising thing is their gravity, while it's incredibly strong if you get really close, it isn't actually any different from any other object with the same amount of mass once you're a decent distance away.
Okay, hang on. So let me get this straight. If our sun right now magically turned into a black hole but kept the exact same mass, what happens to Earth?
Earth and all the other planets would just keep orbiting exactly like they do now. We wouldn't get sucked in at all.
Seriously?
Seriously. The only real difference for us would be, well, sudden darkness and it getting very, very cold very fast.
Okay, that's a pretty big difference. But orbit-wise, we're fine, so the sucking only happens if you get too close.
Exactly. You only get truly captured, as it were, if you cross a very specific boundary. We call it the event horizon. We'll definitely get into that.
Right.
But what really makes these things so fascinating and why physicists are so obsessed with them is that they push our understanding of physics right to the absolute edge.
The edge.
Yeah, they're like nature's ultimate laboratories. You've got Einstein's theory of general relativity, which explains gravity on the grand scale, smashing head-on into quantum mechanics, the rules that govern tiny subatomic particles.
And they don't play nicely together.
Not at the heart of black hole, no. Our equations, our best descriptions of the universe, they just break down. They stop making sense. It signals we're missing something fundamental, probably a unified theory.
Wow, okay. That really sets the stage. So let's dive in. Let's take a tour of the different kinds of black holes that are out there. Maybe start with the common ones.
Good idea. We could start with stellar mass black holes. These are the relatively smaller ones, though still incredibly massive compared to, say, a planet.
And where do they come from?
They're born from the death of truly massive stars. We're talking stars maybe 20 times the mass of our sun, or even more. When a star that big runs out of fuel for nuclear fusion.
The fusion that holds it up against gravity.
Exactly. When that stops, the star's core collapses catastrophically under its own weight. This collapse often triggers a massive explosion called a supernova, blasting the star's outer layers into space.
A spectacular ending. But what about the core?
Well, if that collapsing core is massive enough, if it's above a certain limit called the Tolman-Oppenheimer-Volkoff limit, then nothing can stop its collapse. Not even the pressure of neutrons packed shoulder to shoulder.
So it just keeps collapsing.
It keeps collapsing into a black hole. Basically, if the core is too heavy to become a neutron star, which is already insanely dense, gravity wins completely.
Right. So how massive are we talking typically? And how big are they physically?
They usually range from about, say, 3 times the mass of our sun up to maybe 100 times. But all that mass is crushed into a region potentially no bigger than a city.
The mass of 100 suns in the size of a city. That's just hard to wrap your head around.
It really is. The density is phenomenal.
But if they're black and points of no return, how do we even find them? We can't see them directly.
That's the million-dollar question in black hole astronomy. Often we find them indirectly. Many are in binary systems, orbiting a normal star we can see.
Ah, so we watch the companion star.
Exactly. We look for a star that seems to be orbiting. Nothing. We see it wobble or move in a way that implies a massive unseen partner pulling on it. Or sometimes the black hole pulls gas off its companion star.
And that gas does something.
Oh yes. As that gas spirals toward the black hole, it forms a disk. It's incredibly hot, millions of degrees, and emits intense X-rays. So we look for those X-ray sources.
Okay, so we look for wobbling stars or intense X-ray sources. Got it. Now, from these stellar mass ones, I know things scale up a lot.
They scale up dramatically. To the supermassive black holes, these are the real giants, the monsters of the cosmos.
Millions or billions of times the mass of the sun.
That's right. Millions to billions. And we find them, remarkably, at the heart of almost every large galaxy we've looked at closely, including our own Milky Way.
Our own Sagittarius A, right? Sitting right there in the galactic center.
That's the one. SGRA, we call it. About 4 million times the mass of our sun. And its presence profoundly affects the galaxy around it.
How are these behemoths even formed? Is it just lots of smaller ones merging?
That's one leading idea. Maybe they started from stellar mass black holes that merged over billions of years, or perhaps from the direct collapse of huge gas clouds way back in the early universe. Honestly, it's still an active area of research, a bit of a puzzle.
But we know they're there.
Oh, absolutely. And we're realizing they're not just passive blobs of mass. They seem to play a crucial role in how galaxies evolve. They can trigger bursts of star formation, or they can blast out jets of energy that shut down star formation. They're like cosmic architects or maybe conductors.
Shaping their galaxies. And size-wise, SGRA is 4 million solar masses, but you mentioned billions.
Yes. M87, the black hole, famously imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. And there are even bigger ones known, like in the quasar TON 618, estimated at a staggering 40 billion solar masses.
40 billion.
The scale is just immense. Their event horizons of points of no return can be millions, even billions of miles across. The disks of gas swirling around them can be the size of our entire solar system.
You mentioned an analogy earlier about the Milky Way and a raisin.
Ah, yes. So to give a sense of scale, if you imagine our entire Milky Way galaxy scaled down to the size of, say, North America,
Okay.
then Sagittarius A, our supermassive black hole, would be roughly the size of a single raisin, sitting somewhere in the middle, maybe Kansas.
Wow. That really puts the emptiness of space and the concentration of mass into perspective.
It does. And the evidence for them is strong, like the relationship between a supermassive black hole's mass and the speeds of stars in the galaxy's central bulge the M-sigma relation. It shows they grew up together somehow.
Okay, so we have stellar mass and supermassive. Is there anything in between?
There is, or at least we think there is. These are the intermediate mass black holes, or IMBHs. They're sort of the missing link in the black hole family.
Missing link, why are they important?
They're really important because they could help explain how supermassive black holes get so big. It's hard to get from, say, 100 solar masses directly to millions or billions. These IMPHs, maybe ranging from 100 up to perhaps million solar masses, could be the stepping stones.
But they're hard to find.
Incredibly elusive. Finding solid evidence is tough. But there have been some really promising candidates found, like potentially one near the center of the globular cluster Omega Centauri.
A globular cluster? What's that?
Think of it as a huge, tightly packed ball of hundreds of thousands, sometimes millions, of very old stars, all orbiting each other. A dense environment where maybe an IMBH could form and grow.
And finding one takes patience.
A huge amount of patience, yes. It often involves tracking the precise movements of stars very close to the suspected center of the cluster over many, many years. You're looking for that telltale gravitational influence from something you can't see. Decades of data sometimes.
Cosmic detective work indeed. Okay, so we have the family portrait. Now, let's get closer. Imagine we're journeying towards one. What's the anatomy? What do we encounter first?
Right, the guided tour. Well, probably the first thing you'd notice, long before you get to the black hole proper, is the light show, the accretion disk.
This isn't part of the black hole itself, you said.
Oh, it's the material falling into it.
Yeah.
Gas, dust, maybe the ripped apart remains of a star that got too close. Because of angular momentum like water swirling down a drain, it doesn't fall straight in. It forms this vast, flat, rotating disk.
And it's bright.
Incredibly bright. The friction and compression in this disk heat the material to millions, even hundreds of millions of degrees. It glows fiercely, especially in high-energy light like X-rays. Often, this disk is the only reason we even know a black hole is there.
That's what we see.
That's what we detect. And it's not uniform either. Because it's spinning so fast, relativistic effects become obvious. The side spinning towards us looks brighter and bluer. The side spinning away looks dimmer and redder. It's called Doppler beaming.
Like the sound of a siren changing pitch as it passes.
Exactly like that, but with light. A spectacular and very dangerous place to be.
Okay, so we navigate past this blazing, swirling disk. What's next?
Next, you reach the boundary itself, the event horizon. This is the defining feature.
The point of no return.
Precisely. It's the specific distance from the center where the escape velocity, the speed you need to get away, becomes equal to the speed of light.
And since nothing can go faster than light,
nothing can escape. Once you cross the event horizon, every possible path you could take, even one aimed directly outwards, inevitably leads towards the center. Space-time itself is flowing inwards faster than light.
Is it like a physical wall?
No, not at all. It's not a surface you'd bump into. For someone falling in locally, they might not even notice the exact moment they cross it, especially for a supermassive black hole where the tidal forces aren't immediately extreme.
What? So you wouldn't notice, but someone watching from far away would?
Yes. That's the weirdness of relativity. From a distant observer's point of view, as you approach the event horizon, your clock would appear to tick slower and slower. Your image would get redder and dimmer. seeming to freeze just outside the horizon, taking effectively forever to actually fall in from their perspective.
Gravitational time dilation. Wow. Okay.
Yeah.
But the person falling in experiences time normally.
Locally, yes. Their own clock ticks just fine as they cross the horizon. It's the difference in gravitational potential that causes the discrepancy between the infalling observer and the distant one.
Fine bending. Okay. So you cross the event horizon. Where do you end up? What's at the very center?
According to general relativity, you end up at the singularity.
The point of infinite density.
That's the prediction. A point where all the black hole's mass is crushed into zero volume and space-time curvature becomes infinite. Now, whether it's really a physical point or if quantum effects take over and prevent true infinity, that's where our physics breaks down.
So we don't actually know what's there.
We don't. The singularity marks the place where general relativity ceases to be a complete description. We need a theory of quantum gravity, one that combines both relativity and quantum mechanics, to truly understand what happens at the heart of a black hole. It's one of the biggest mysteries in physics.
So these objects literally bend reality. Let's talk about some of those effects. You mentioned light bending, gravitational lensing.
Yes, because mass warps space-time and light follows the curves in space-time, a black hole's immense gravity acts like a lens. It bends the path of light coming from objects behind it, from our perspective.
What does that look like?
It can create weird distortions. You might see multiple images of the same background galaxy, or distant stars might appear brighter, magnified. If the alignment between us, the black hole, and a background object is perfect, the light can be smeared into a complete circle called an Einstein ring, surrounding the black hole's shadow.
We've seen pictures of that, haven't we? The Event Horizon Telescope images.
Those images show the shadow cast by the event horizon against the glowing gas behind and around it. And lensing plays a role in shaping that image, absolutely. Astronomers also use this lensing effect as a kind of natural telescope, using the gravity of foreground objects, including black holes or galaxy clusters, to magnify the light from very distant, faint galaxies we couldn't otherwise see.
That's clever, using the universe's own quirks. Okay, and we touched on time dilation near the event horizon.
Right. Time literally runs slower in stronger gravitational fields. The closer you get to the black hole, the slower time passes relative to someone far away. It's a real effect, predicted by Einstein, and extreme near a black hole. If you could orbit close to one and return, you'd be younger than someone who stayed on Earth.
The ultimate, though perhaps slightly terrifying, anti-aging technique.
Theoretically. Though there are other effects to worry about.
Like the wonderfully named spaghettification.
Exactly. This is all about tidal forces. Gravity pulls more strongly on things that are closer. So, as an object, let's say, hypothetically, an astronaut falls feet first towards a black hole.
Uh-oh.
The gravitational pull on their feet is significantly stronger than the pull on their head. This difference in force stretches the object vertically while squeezing it horizontally.
Like pulling spaghetti.
Precisely. You get stretched into a long, thin strand. And interestingly, this effect is much more pronounced outside the event horizon for smaller stellar mass black holes because the gravity changes more steeply over shorter distances. For a supermassive one, you might cross the horizon before the tidal forces become fatal.
Small comfort, perhaps. So, given they're invisible and often distant, how do astronomers actually track these things down? We mentioned watching stars.
Yes, observing stellar orbits is key, especially for supermassive black holes like SGRA. We've tracked specific stars, like one called S2, orbiting the galactic center at incredible speeds, thousands of kilometers per second whipping around an empty point. The only explanation is a huge unseen mass there.
S2 completes an orbit in just 16 years, right? That's fast on a galactic scale.
Astonishingly fast.
Yeah.
And precisely mapping those orbits lets us calculate the mass of the central object very accurately. It was definitive proof for SGRA.
And then there are the X-rays from the accretion disks.
Exactly. That superheated gas is a dead giveaway. Instruments like NASA's Chandra X-ray Observatory are brilliant at spotting these bright X-ray sources, which often pinpoint black holes, especially those actively feeding on companion stars or gas clouds. Chandra's helped find potential IMBHs and even watched SGRA have flares or meals.
So we can see their influence, see their food getting hot. What about detecting the black holes themselves, especially when they merge?
That's where gravitational waves come in. This was a game changer. Observatories like LIGO and Virgo are essentially giant microphones listening for vibrations in space-time itself.
Not light, but ripples in space.
Exactly. When truly massive objects, like two black holes or two neutron stars, spiral into each other and merge, they create these waves, these ripples that travel outwards across the universe at the speed of light.
And LIGO detected them.
Yes. The first detection in 2015, GW150914, was from two stellar mass black holes merging. It was direct proof Einstein was right about these waves, and it opened a whole new way to observe the universe, especially these violent dark events.
Yeah.
We can now hear black holes colliding billions of light years away.
Incredible. From seeing orbits to seeing X-rays to hearing space-time ripples and finally actually imaging the silhouette.
That's the Event Horizon Telescope,
Yeah.
EHT. It's not one telescope, but a global network of radio telescopes all linked together. By combining their data, they create a virtual telescope effectively the size of the Earth.
To get the necessary resolution.
Precisely. To resolve something as small and distant as the event horizon of M87 or even SGRA. In 2019, they released that first iconic image of M87's shadow, the dark central region where light can't escape, silhouetted against the glowing hot gas swirling just outside the event horizon. Then came the image of SGRA in 2022.
Not seeing the black hole itself, but its shadow.
Exactly. Seeing the edge of the abyss, defined by the light that just barely skirts it. It was a monumental achievement, confirming our theories in stunning visual detail.
It really feels like we've gone from pure theory to actually observing these things in multiple ways now.
We absolutely have. It's a golden age for black hole research.
So as we wrap up this deep dive, it's clear black holes are far more than just cosmic vacuum cleaners.
Definitely not. They're fundamental parts of the universe's structure and evolution. Stellar mass ones are the endpoints for massive stars. Supermassive ones anchor galaxies, and they all bend space and time in the most extreme ways imaginable.
We've looked at the different types, journeyed metaphorically from the blazing accretion disk, past the point of no return event horizon, towards that unknowable singularity at the center.
And we've seen the ingenious detective work astronomers use, tracking stars, catching X-rays, listening to gravitational waves, and even taking pictures of their shadows with an Earth-sized telescope.
But the biggest questions still remain, don't they?
Oh, absolutely. What really happens inside the event horizon? What is the singularity truly? Do black holes eventually evaporate through Hawking radiation, as theory suggests? And how do they fit into a final theory of quantum gravity?
They really are the ultimate frontier, where our current understanding meets its limits.
Exactly. They're the place where gravity and quantum mechanics have to somehow reconcile. Studying them pushes us towards that deeper understanding, towards potentially a completely new picture of reality. The mystery continues.